Let's dive right into the technical application of IQAGREEN in industrial thermal equipment. This product functions in two distinct environments: cooling systems and steam generation systems. Understanding this application really comes down to mapping out exactly how it protects critical infrastructure.
So, what actually happens when solid particles continuously recirculate through heat exchangers? Well, the operational consequence is severe. In any industrial system relying on water, impurities present a constant battle. Untreated feed water inherently carries dissolved and suspended solids, and adding environmental air into the mix introduces even more airborne particles. Left unchecked, these particles continuously recirculate.
This failure progresses in distinct stages. First, sludge accumulates directly inside the heat exchange areas. If ignored, those retained solids transform into rigid, unyielding scale. We're talking about hardened deposits composed mostly of calcium, magnesium, carbonates, and silica. The ultimate operational result is a severe and highly visible loss of heat exchange efficiency that can literally cripple an industrial process.
Here is the structure of this analysis. 1. Cooling systems application. 2. Steam systems application. 3. System differences. 4. The descaling process. And finally, 5. Key takeaways.
Section 1. Cooling systems application. The analysis begins with open cooling circuits.
The primary equipment architecture for open cooling circuits relies on cooling towers and evaporative condensators. These are units utilizing fill or coils where the actual heat exchange happens. Often, these primary units are supplemented by additional heat exchangers. This includes centrifugal chillers, shell and tube exchanges, or plate exchangers. The operational threat here originates from a combination of factors. To conserve physical state and extend useful life, feedwater and environmental air must be managed. Feedwater solids and environmental air particles physically combine to generate internal sludge. Simply put, the more solids present, the greater the accumulation of sludge inside the equipment. To treat this, the solid product packet is placed directly in the basin. Its packaging allows it to dissolve progressively. It acts chemically in two main ways. First, an anti-corrosive action occurs as the pH of the medium increases. This creates a coating that acts as a barrier to prevent metal corrosion. Second, a dispersant action separates the solids in the water. This prevents hard-scale compounds from forming. Instead, it creates a soft, removable sludge that precipitates right there in the basin for rapid extraction.
Shifting environments entirely presents a new question. What is the direct operational consequence of omitting boiler blowdowns? This introduces a completely different set of thermal challenges. Here, pressure and vaporization change the rules of the game completely.
Section 2. Steam systems application. The mechanics of steam generation present unique challenges.
Two main boiler architectures are used for heat generation. The fire tube boiler operates with combustion gas flowing inside the tubes, which are completely flooded and surrounded by water. This is by far the most common industrial standard. The water tube boiler operates as the exact inverse. Water circulates inside the tubes while the combustion gases surround the exterior. Regardless of the boiler type, the fundamental operational challenge remains exactly the same. Makeup water always brings dissolved solids. However, dissolved solids cannot vaporize. As the water turns to steam, those solids are left behind. If they're not eliminated, they will concentrate and accumulate directly on the boiler floor and the surfaces of the tubes. The treatment controls this harsh environment by being dosed directly into the condensate tank. This feeds directly into the boiler, allowing the treatment maximum residence time. Once inside, it generates an alkaline medium and creates a protective coating on the surfaces in contact with water. This shields them from oxygen corrosion. Simultaneously, just like in the cooling systems, a dispersant action separates solids. This prevents rigid scale and precipitates them into a soft sludge at the bottom of the boiler. It's important to note that treatment does not stop sludge generation. Makeup water will always bring impurities. Instead, the treatment transforms those solids so their elimination is rapid and easy. Elimination occurs through strict bottom blowdowns. Omitting those blowdowns means sludge accumulates, and eventually, that causes the very scale the treatment aims to avoid. Section 3. System differences. The operating mechanics explicitly contrast. In cooling systems, secondary contamination comes from environmental air mixing with water, and the product is applied via direct packet dissolution in open basins. In steam systems, the primary mechanical issue is vaporization concentration. That is, solids left behind when water boils. And here, the product must be physically dosed into the condensate tank. So two different thermal environments dictate two specific methods of application.
Now, how does the treatment interact with pre-existing rigid scale deposits in either system? When heat exchangers or boiler tubes are already severely compromised before treatment begins, a specific remediation phase is absolutely required.
Section 4. The descaling process.
This standardized descaling mechanism works identically in both cooling and steam systems, operating in distinct chronological phases. Step 1 begins with the chemical hydration of the superficial scale layer. Step 2 utilizes this hydration to drive the progressive detachment of those hardened scale plates. Step 3 requires patience. This process typically takes 4 to 6 months to see full results, depending entirely on the gravity of the initial situation. The ultimate expectation upon opening the equipment is a system entirely free of scale and corrosion damages.
Section 5. Key takeaways.
3 final operational protocols dictate success. First, the treatment effectively protects equipment by physically preventing scale and blocking oxygen corrosion through a specialized barrier. Second, proper physical application and strict adherence to blowdown regimens are absolutely mandatory. The product makes the sludge removable, but physical removal remains necessary. Third, ultimate success requires continuous teamwork between the facility and the technical service, as specific operational conditions will always affect product efficiency. This leaves one final thought. If a facility treats thermal equipment maintenance as an afterthought, what invisible damage is currently costing heat exchange efficiency right now?